Harris's Pioneer Award in 2023. He also received the Qualcomm Innovation Fellowship in 2021. Thanks for joining us, Ankit. Take it away.
Thank you so much, and thanks for inviting me again, Sacha. So, so today I'll be talking about some of the work that I've done at NVIDIA after my PhD. So um, it's a series of two works, and I've tried to put together, and they are like um, improvements over the prior work. So I've tried to put together a set of slides going over our idea and what we're trying to achieve here. So this is focused on like 3D manipulation and our use of how do we use view transformers? Like how do we bring in the use of image transformers for doing some like 3D tasks in robotics. So this work, I would, so this work has been like a team effort. Especially, I would like to acknowledge some of them like Jia, Yeje, Vals, Yuve, and Dieter. So all of them are research scientists and manager at NVIDIA Seattle Robotics Lab. Okay, so um, so before I begin, like what we do, I just wanted to give a quick sense of like what are we trying to accomplish here? So these are like the kind of tasks we want robots to solve. So these are, we refer to them as like 3D object manipulation tasks because they go beyond just the um, 2D plane or the 2D plane or the table, right? So they involve things like um, maybe like putting up a bulb somewhere or like opening drawers. So putting things in shelves. So like these are beyond like the typical pick and place task. And that is why we refer to them as 3D manipulation. Now, um, now when around like 1.5 year back when we started working on this, there were like two popular representations for doing like 3D manipulation. So uh, one representation or one way people uh, did some manipulation was like using just like images, right? So you have like RGB or RGBD images from the camera, and then you can process it in some way to predict, let's say, man actions. So it involves some of our works like I4 and also this popular work called Transporter Net, which was essentially transporting objects on the 2D plane. So as I said before, these cannot handle 3D or don't work well in 3D. You can have like, you can do some tricks like predicting the Z dimension of your actions, but they don't really work that well. However, these methods are very scalable in the sense since they're just consuming images, they are like very fast to train, and like even at inference time these methods are very fast, and they're fast as compared to methods which use and create an explicit 3D representation and then process that explicit 3D representation. So here I've listed two of the popular works uh, at that time. So one of them is Perceiver Actor. So essentially, what Perceiver Actor does is uh, given uh, given RGBD images, it creates like this voxel. So it reconstructs a voxel of the scene, and then it processes that voxel through a transformer um, to make predictions. And similar in vein with C2F which uses this bottleneck structure to process voxels. So these methods, contrary to the 2D methods, these methods are generally found to work better for 3D manipulation. However, uh, they've not been that scalable, right? This is because these explicit methods are constructing something which is n cube of the resolution, right? Because these voxels or any explicit representation of the scene is n cube in where n is your resolution. Now the question we ask is, um, can we avoid um, can we avoid doing this n cube this creating this input and then processing this n-cube resolution representation without sacrificing performance. And one of the key ideas that we came up with is that instead of representing the scene through this explicit uh, voxel representation, can we represent it through a set of images? So here, the set of images are these uh, orthogonal rendered images. So these are not real images from the camera, right? So these are not something that you have to set up in the environment, but you can always render from do rendering and create these images. And these images uh, are complete in the sense they give you the complete picture of the environment, so you're not missing on any information. But at the same time, now instead of requiring to process this huge intermediate and cube representation, you can still use a lot of the 2D techniques to process it. So these are like very scalable. So they become very scalable, while at the same time, they perform equally well or even better than explicit 3D representations, because you can train them much longer, you can scale them much better and things like that. So yeah, so that's like the main, I would say, main idea from which this line of work, these two papers come from, and essentially they're trying to exploit this alternative representation to do 3D manipulation, and I'll explain how. Okay, so this is the first work. So it's called RVT, Robotic View Transformer for 3D Manipulation, and we presented it in it should be 2023. So we presented it in Core 2023. So now let me give a very brief overview of the pipeline, right? So here the task is, so let's say you have a scene, and then you have an instruction like stack the teal blocks. So there are multiple of these teal blocks, and the task is, okay, stack them together. The first thing that happens in the pipeline is that given the task, you would have, let's say, input RGBD images. So this could be one image or it could be multiple images. The framework is flexible to either use one or multiple of these RGBD images. The first step in the pipeline is to just reconstruct a point cloud from the given RGBD images. So we assume knowing, let's say, the camera intrinsic, extrinsic, so the cameras are well calibrated, and from there we can, let's say, reconstruct a partial view of or point or point cloud of the scene. Then, as I was explaining, and as I was explaining before, uh, instead of like directly consuming this point cloud, like instead of like converting it to voxels and consuming it, or like trying to apply some other techniques, what we first do is simply render these images through orthogonal views. And these orthogonal views are um, these orthogonal views are like at the square at this cube locations, right? So they are like right on top, right? So this gives you a very nice overhead view, and then right, front, left, right, and back. Um, what we do is, like, given these orthogonal views, we uh, we process them through a transformer, or you could use a CNN. We just use a transformer, which is attending over all the images. Right, so there is let's say there is a CNN or a transformer which takes in all these images and then spits out a heat map for all of the individual images. And what these heat map locations indicate is that where the for that particular view, where should the gripper go? So you could see, like, this is a heat map representation. This is multimodal. Uh, it is automatically multimodal, right? As you can see in the scene, there are multiple teal blocks, and we can see that there, okay, the network is predicting heat on in multiple spots, which are like the teal, which are that teal colored blocks, and similarly on this on the front on the front view, it's predicting these sets of heat map. Now, given these 2D heat map predictions, what we do is we again have to take actions in 3D. So we go back into the 3D space from the image space. And this is essentially done by like for each 3D point, we calculate the 2D predictions, and we do a very simple thing. We just average out the 2D predictions for each 3D point, right? So for example, at this 3D point, we see its corresponding heat map prediction at every of these images, and we take the average value, more which is a very simple averaging scheme. And what this gives us is now a 3D heat map of where the gripper should act. So this, and one thing to notice is this, again, this 3D heat map is also multimodal. So we can see that on all the teal blocks, there is a heat map saying that, okay, you should go, the gripper should go here. And this represents the gripper location. And what we also need to do is to predict the gripper rotations and the gripper state. So this is predicted by taking the predicted location and the corresponding features from the feature map. So I only showed the predicted 2D heat map, but there is also a corresponding tensor which is used to predict these heat maps. And so we can take features from those corresponding locations and use those to predict, let's say, things like rotation and whether the gripper should close or not. And then we just execute that action. So we just say, okay, the gripper should go there. And that is so this is like a key point based manipulation scheme that also the prior verse. We're also doing this key point based manipulation scheme where you predict like some of these sequence of key points. So here what I've shown is like, given a scene and an instruction, how do you predict the next key point action? And this is then updated, right? So as the gripper goes there, we update the scene instruction and run the pipeline again to predict the next key point. Right, so these would be some series of actions for stacking the teal block there. Okay, I'll actually take a moment to see if there are any questions about the pipeline, or if the general idea is clear. Yeah, is there any confusion here?
Questions? I have one. Okay, Miguel?
Yeah, so the virtual images, are those generated from, I don't know, an error Gaussian splitting approach, or are they just sampled now from the simulator as you have this privileged information?
Yeah, so no Gaussian splatting, nothing. So this is just explicit rendering operation.
I see.
But it's not using privileged information, like it's just using the point cloud that's been generated, right?
Oh, it's for the point, I see.
Yeah, it's from the point cloud. It's not using any like other information than the point cloud.
All right, got it, thanks.
In practice, how many input images do you actually need for this to work well? Do you have experiments where you only have like a single RGBD or maybe two RGBDs, like limited RGBDs?
Yeah, so like in real world, we just use one RGBD.
You only use one RGBD? Okay.
Yeah, so I'll go over those. Yeah, but that's a good question.
Okay, because I remember reading this paper a couple months ago, and I'm really interested. I mean, manipulation is great, but I'm really interested also in the mobile setting where you have a mobile manipulator, right? And in those cases, it's very hard to have, like, assuming you have different cameras to look at your scene at all times is not very feasible. So yeah, okay, knowing that this works with one RGBD is great. Okay.
Did you guys think about a nerf thing for this instead of a point cloud?
So there have been extensions of this work which try to use like a nerf for like rendering and things. So we found, so the issue there is like that's slow, right? Like constructing at least at that point of time, it was like slow. So here, so this is like a very fast operation, right? So this is just explicit on the GPU fast rendering thing. So that also makes our method very fast. But I'm sure like there could be extensions where like and then there have been extensions where people try to like visualize create this um, these images, yeah, from partial views.
Great, thanks.
Okay. Okay, I'll move ahead. So yeah, so like so that's the method, but like what is the like to make it more concrete, right? Like what's the setup? What are we training, testing things on in the real world? So it looks like this. So we I describe it as like few short multitask. So we collect, let's say, 10 demonstrations for different real world tasks, right? So for example, here one of the tasks could be putting the marker in the bowl or putting the marker in the cup, right? And then the marker the task itself is specified by language, and so so we have like um, yeah, so we have like a single policy. We want to train a single policy that can handle multiple of these tasks. So here, like the 5 tasks that we were looking at is like stacking block, placing in shelf, like opening drawer and putting something in the drawer, um, pressing the sanitizer or putting some marker in the bowl. And each task has its own variations, right? So it could be like put the blue marker in the bowl or put the green marker in the cup and things like that. And that variation itself is specified by language. And as such, I was asking, there's a single RGBD camera as input. So this is the RGBD camera we were using. So this method surprisingly works really well. So here I'm showing like real time execution on like several of these tasks, and with just 10 demonstrations we are able to get like good like 82% kind of accuracy in all of these tasks, and they are each of the tasks in itself just have like 10 demonstrations. So in general, this method is good at like uh, yeah, it's good at like getting a few demonstrations on some task and starting the robot to work really quickly. And there's like there is definitely we see generalization, and like we change the variations of the location of the object on the workspace and pose of the objects and generalize as well in those setups. And we also do simulation testing. So as I was comparing to PerAct. So since we are, instead of doing this explicit processing, we do this in images. So we are able to increase performance as well as increase like inference speed. And I think the big improvement we got was like around 36x improvement in training time. So it's much easy to train because it's just training on images. Now those are the results, but I think like it's good to look into like what are the some key takers, and hopefully it will answer some of the questions that people might have had about like the method. Why are you doing something? So one question I always get is why do you re-render stuff? Why don't just use the original input RGBD images, right? So there are many advantages. so we test that, right? So that's like the first thing we did. We just use the input images and do the same prediction and things like that. So there are, I think there are two key reasons. One is this inductive bias. So at least in manipulation, having an overhead view, right on top is very useful, and that is something we won't get in a real. That's like it's hard to get like a direct overhead view in a real setup, right? Even in autonomous driving, they've seen that okay, um, they try to like construct an overhead view and try to reason there. So even in manipulation, that's the case. And these are like these completely aligned views, they seem to be like really useful. And that's like the inductive bias that this this re-rendering step allows us, right? So it allows us to take any view that we want, um, and we are not constrained by the hardware, right? So even if we have, let's say, one RGBD camera, like we had in the real world, we could still have these multiple views by this re-rendering step, right? That's another advantage. And the other thing, it also allows us to do 3D augmentation, right? So like the real images, we cannot change, we cannot apply a 3D augmentation in the scene and change the real image. But since we come to this point cloud space, what we could do is like we could rotate the point cloud, we could like do any 3D operation on the point cloud, and then we can easily re-render the image and train our network. So this using the virtual image allows us to do these kinds of 3D augmentation, which are like non-trivial to directly simulate on the real image. It so yeah, so that, and also this comes up in when we check the performance. Another thing, another detail that I didn't talk about much was that we found that instead of using, so when we are re-rendering the images, right? So there are two kind of projections that we could use. So one is the perspective projection, which is like what our eye sees, what cameras usually capture, right? So so perspective projections, things are um, things are changed by the perspective transformation, right? So if something is far, it would look small. If something is close, it would look big, right? But in our case, we found that instead of using this perspective projection, we could use an orthographic projection where the size and shape of the object is not affected by how far it is. So in perspective projection, if something is far, then its projected shape on the image space would be different, right? So we found that uh, that that is something, if even if when we have like few short settings and things like that, that is something that's harder to learn, right? But in our, we could, but when we use orthographic projection, it gives us this advantage. Um, and we could, it's probably easier for the network to reason when we have like orthographic projection. And this advantage might go away when we have like lots of data to see, but like at least in robotics, it gives us like this uh, initial boost. And some other cool things we could do when we are doing this re-rendering is that we could add additional channels, right? So one channel that we add in our network is this point correspondence channel, because for each point across images, we don't want the network to waste its capacity in figuring out the correspondence of the point, right? Like this is the same point in different views. Now this information we can directly feed into the network by simply rendering, instead of rendering RGB, we can render the XYZ values, right? So if each point has a unique XYZ value in the 3D space, and if 2 points in two different images have the same XYZ value, that means they are the same point in the 3D space. So these are some things we get some minor boost by adding this, but like these are some things we could do. Some new channels we could add, new information we could add if we are doing this re-rendering. Right. So here are some of the key ideas that I wanted to cover, and this would cover most of what I wanted to talk about RBT, and I'll actually wait to take any questions here if there are any.
I have a question.
Yes.
So I'm not entirely sure I'm understanding the distinction you're making with the orthographic projection thing. Like, wouldn't the challenges with perspective projection also be solved by just keeping the camera always at the same place relative to the scene? Like, wouldn't that be equivalent?
So the camera is at the same place relative to the scene in this comparison. So this is just comparing even in the virtual view whether we take a perspective versus orthographic projection.
So by taking the orthographic projection, you're really just taking all the points in the point cloud and then just like projecting them down like orthogonally onto the scene. I just don't understand why this would change. Like, so I understand that like with the perspective projection, you have a loss of scale and things like that. But oh, I see. So this is going to be scale. It's going to be scale invariant, I guess, in this case.
Yeah,
You're
it's
always going to get.
kind of like distance invariant, like
Yeah, okay, I see. But I still don't understand why if you just decided on what that distance was going to be and always kept it the same, then why the perspective projection approach wouldn't work.
so it would work, it just doesn't work as well.
Yeah, I guess that's what I don't understand is what's the difference between an orthographic projection and the perspective projection, assuming that you always render like from a camera position that's fixed and the same distance.
Yeah, so it always renders from the camera position that's fixed. But then let's say you have two different episodes, right? In one episode is the same object, but it is closer. And in another episode, the object is farther, right? So it would create
I see.
different kind of images. It's just easier for the to reason. Yeah.
That makes sense. Thanks.
Yeah, it's a good question. Okay, so let me go ahead. So now that's what like, okay, so we have seen RBT, and there are also other methods like diffusion policy, VQBED. So these are methods that can learn from few demonstrations, right? And why do we need to then yeah, so what's the new thing with like improving these methods? What are you trying to gain, right? However, like if you're considering some tasks which require very high precision, we generally resort to using like RL to make these fine adjustments and then things like that. Now the question is, can we make behavior cloning methods such that they can also handle this high precision requirements? Like this is inquiry is about how precise can we make this behavior cloning method so that at least the task that the RL or the fine tuning or the fine adjustments that we have to make, that's very minimal as opposed to the current way of doing things where a lot of the heavy lifting has to be done by like some RL policy, which is making fine adjustments, or like some other kinds of motion planning primitives that have to make these fine adjustments. So we want to see how precise can you make these methods, behavior cloning methods. So this is a recent work which we presented at RSS. So essentially, this is the same kind of our same setup as like the RBT, and here I'm showing some of the tasks that we could do with this method, like inserting peg or inserting plug-in socket and things like that. And this kind of like shows how precise the predictions are predictions are within like millimeter range things. Now how do we go from RVT to RVT2? So one of the key architectural change that we made was instead of just doing this as single scale prediction, what we do is now we make this design multi-scale, right? So we have like the same branch as RVT in the first layer, and then based on the prediction made in the first layer, what we could do, since we are re-rendering stuff, right? We could now re-render images at that specific location, right? At the specific prediction that is made in the first stage. And we can create that now a same pipeline that takes on these virtual views at these re-render location, make like a very precise prediction. So this was like the key architectural thing, and this gave us like a huge boost in like on benchmarks and also in real world, as I was showing like some of the real world results. Some we did a lot of like other improvements, but I'm just mentioning three of them here, and also what what we did was like we sped up RVT a lot, so it was already much faster than prior methods, but we continued to improve it, and instead of like using off-the-shelf solutions that have like a lot of flexibility, but they also come with a lot of bells and whistles. So we wrote down like because our rendering is like very simple. It's just taking point cloud, projecting onto these planes. So we wrote out this renderer in CUDA, and that like improved our training speed by a huge amount. Because this is like a custom renderer wrote only for this specific use case, and does nothing else, but helps us a lot. One other thing that I like about this method is that we also added this general technique. I think a lot of other places this technique could be used. Is this convex upsampling? So let me try to explain it. So essentially, whenever we have like upsampling layers in let's say transformers, upsampling layers in convolution networks, we use this deconvolution operation, right? Now instead of using this deconvolution operation, we could use an alternate operation, which is this convex upsampling, where each value at a higher resolution is essentially just a convex combination of values at the lower resolution, where the combination is essentially learned by um, where the convex weights are kind of learned, and learned and feature dependent, and they are learned by the previous layer. So this layer, instead of how does this layer save us memory and speed, is that generally when we do the deconvolution operation, we have these huge tensors, at the high resolution, right? So we would have height, width times, let's say, height, width, and feature sizes. But we don't need that high resolution tensor. What we generally need is some prediction from that high resolution tensor, right? So let's say we would predict a heat map from there. So then we have this height, width times feature, and then we go to something which is like height, width times 1 or height, width times 2 or something like that, right? And so what this convex operation does, it kind of like avoids creating that big tensor, and that saves a lot of memory, because what it is doing is that it is directly trying to predict things from the low resolution features. And this trick was also This was introduced by Teed et al. In the paper Raft, which was for optical flow, and we just incorporated it here and that, like without affecting performance. It helped it with speed, and we use it in RBT2 as well. RBT2 as well. No, I already showed you some, like I'm almost at time, so I already showed you some results in the real world, and since then there have been more works, but with RBT2, this simple design changes, we are able to create a system which is like the best performing as well as like the fastest, both in inference and training speed. So like so we started with the PerAct used to take like 16 days to train. Now we could train the same thing with same hardware within 1 day. And while at the same time going from 50%, we went now to 82% in a matter of 1.5 years. So that's good to see, and there's like now even more work in this domain. Okay, so I'm at time. So just some key takeaways, and then I'll open the floor for more questions. So in general, RBT and RBT2 are these general methods for manipulation, and you find them to be more accurate and scalable than prior state of the art. And one of the key ideas in that motivated this design was this use of orthogonal views to preserve the geometry. So like and then process those views. And I'm sure this could be applied in other domains as well, where we want to preserve the 3D information while also making something very fast and scalable. And we find that this method works well in the real world and on like precise tasks with very few demonstration requirements. So yeah, that would be it, and I'll be happy to take any questions. Thank you.
Okay, yeah.
Thank you, Ankit. Okay, questions?
I have more questions.
You have more questions?
Yeah.
Yeah.
So, in the zooming in part, are you like limited by the actual resolution of the point cloud that you have, or are you actually going like finer resolution than the actual resolution of the point cloud that you have? It would seem like for those very precise tasks that you showed, the point cloud that you would get from a standard off-the-shelf RGBD camera may not be even sufficient to capture some of the fine details that you would need. So are you using some fancier sensor, or are you actually, or am I wrong? Or are you actually like upsampling beyond the resolution of the point cloud that you're generating from the camera?
Yeah. So we are not doing any upsampling, and we are just using, it's no special sensors. It's just Azure, like a normal sensor from Azure. But so we found that to be sufficient, and so yeah, I suppose you could do some upsampling at that location, but we don't do that here. We found even after cropping the resolution or whatever the network was seeing, it was sufficient for it to infer. But I suppose, yeah, like having more sensors, or one other thing could be like using like gripper RGBD, like at that like the gripper camera at that location, and then capturing a new image and maybe creating a higher resolution. That could also be useful, but we don't do that here.
Okay, amazing.
You use the point cloud to generate multiple views. You could also, use a deep learning architecture that takes that point cloud as input directly. Are Are you familiar with works to do that, or why having this kind of virtual view generation would outperform just using the point cloud as input?
Yeah, it's a good question. So there are methods uh, which um, which do that. So for example, I think this method 3D diffuser actor, which does that. So it's able to get similar performance, but it's like much slower. Um, um, yeah, and this is also using there are other things as well. I would say Arc 3D is also one which was directly using point clouds. So yeah, so I think I would say it's not yeah, point cloud would be no less information, right? So it's the same information, but maybe the current architectures are slower. And this just using virtual images is just like faster, more scalable. So I'd say, and this also becomes more critical as we scale up things, right? So let's say here, it doesn't matter that much, but if we are, let's say, processing huge amount of data, in that case, this will become even more critical. Yeah.
Makes sense. And do you actually run your policies at 20 FPS on the robots? Or is this just like the max FPS you can get with the model?
So this 20 FPS is what we um, test on the benchmark. So this is the
On the
RLBench
benchmark, yeah, sorry.
benchmark. Um, and also yeah, and this is like the inference speed we could get like on, I think this was on a 3090.
Okay, okay, thanks. All right. And any questions?
I had a question. Sorry, I'm joining remotely, Ankit.
Yeah,
Yeah. Thank you for the presentation. I just had a question about the implementation of your custom CUDA renderer that you showed. So is that sort of dependent on the initial third-person view of your Azure camera, or does it also work if you move that camera around? I guess my main question is like, how does the renderer decide what the correct orthogonal view is?
Yeah, so because the input camera we calibrated, right? So we have like the extrinsics and intrinsics of that camera. So we have extrinsics with respect to the robot base. And so we just use that. So if
Right.
you have like a new location, then the extrinsics would change, and then the
Right.
point cloud
Got
would.
it. Thank you.
okay. And yeah, one last question for me. We had a speaker, I think it was 2 semesters ago, and his opinion was that you don't actually need 3D, sorry, because as you scale models, 3D is like one of the first, like the 3D structure is one of the first things that kind of model figure out as you provide them with more and more images. So I'd like to have your opinion on this kind of at a higher level. Like, do you feel that 3D will be essential for future manipulation policies? I mean, given your line of work, maybe you will say yes, but yeah, I'd like to have your thoughts on this. Like, is 3D necessary?
Yeah, I think that's a debate, right? So my perspective on this is like getting 3D is easy and something we already have, like in robotics, autonomous driving scenarios, right? So that if that information is already there, so it's definitely something we should use. And we still find that these 3D methods are like much better as compared to 2D only methods, because and in terms of their precision and performance. Um, it like I could very well imagine it being the case that okay, if we have tons of data, uh, then the advantage we are getting by explicitly feeding 3D goes away. but I don't see that happening in robotics. That will have that much data that we would be able to learn a good implicit 3D representation and then use of it. And even if, let's say, we have tons of data, even if, let's say, we have lot of data, why not use this extra modality that's like is there, right? So I have, yeah, yes, I would say it is to be seen, and this is I would say also the case in um, like even if you just use 2D images, a lot of these pipelines that just use 2D images still have like some explicit 3D learning, right? So they would do some stereo or something like that to like learn a better representation. So 3D is definitely helpful, right? So if it is coming to you through a sensor, why not use it? That's what I feel. And I at least for the recent advancement, I do think they would play a key role.
Okay.
Maybe in 10 years, 20 years, I don't know. Not, but like, yeah, till then. Makes sense.
Okay. All right. Other questions online? I don't think so. All right. So thanks so much, Ankit. That was a great talk.
Thank you so much. Thank you.
Okay.
Thanks. It was nice to be with you.
Okay. Thank you. See you.
Yeah, bye.